that a charged particle that's actually in a magnetic field, okay, is going to spiral. It's going to spiral around and around and around, okay? So if there's a charged particle, and the particles at the sun, in the solar wind, okay, those particles, pretty much all of them are charged, okay? And so in the solar wind, when charged particles actually approach the Earth, first let's just think of this room, right? Let's pretend we're standing between the poles of a magnet, and that the North Pole is below us, and that the ceiling is a South Pole, okay? Let's assume that the magnetic field is uniform in this room, okay? That it's this giant thing, and just like the parallel plates of something that makes electric field, right? Just how we know that the electric field in the middle is quite uniform. We've mapped this and everything, right? The magnetic field inside the poles of a very large magnet would also be uniform. Now, if I had a piece of iron in this uniform field, to be sure, okay, that piece of iron, as it is here, right? The ceiling, the floor being North Pole and the ceiling being South Pole, okay? To be sure, this side would be a North Pole and that side would be a South Pole, okay? There would be an induced magnetic field in that piece of iron, but the force of attraction here would be the same as the force of attraction there, and so there'd be no net upward or downward force, okay? Yes? And if I took that piece of iron and I rotated it, as long as the iron is like malleable, it's like magnetically soft and not a permanent magnet, if I turned that piece of iron sideways and put it like this in there, the top would just become north and the bottom would be south. And there might be some resistance to my rotating it at some high speed, like that, because it takes work to actually rearrange those magnetic domains. There still would be no net force. In a uniform magnetic field, I wouldn't be sucked up, I wouldn't be sucked down. Okay? As I approach this, though, I would be sucked into this space. If there was ever an inhomogeneity, okay, a place where it wasn't homogeneous, right, then yeah, there would be a net force on a piece of iron. Okay? Now, let's suppose I had a permanent magnet, one where the magnetic poles did not just rearrange themselves, it had an opinion, right? And I put that thing in here like this, and I walked in here and I had this be the North Pole and that be the South Pole. Is that thing going to be happy there? No. No, it's actually going to rotate. This side's going to rotate that way. This side's going to rotate that way until it is then vertically oriented, right? Until this end is north and that end's south, like that. And then there will be no net force. It'll be kind of funny. It'll be sitting there like this and I won't be able to rotate it, but if I drop it, it'll just fall to the floor. Yeah? It'll be able to translate up and down, translate this way, but we will not be able to rotate it easily. Yes? Isn't that fun? That's kind of fun. And then the other thing that you would notice, by the way, if you were in this intense magnetic field, is that if you moved, you actually would have induced electric currents in your brain and you'd actually hallucinate, you'd see things, which is kind of a crazy thing. You'd notice that metal objects, even aluminium, would be hard to move through the field if it's strong enough. And my old student teacher worked at a place in Florida where they had intensely strong magnetic fields, and he said that picking up the aluminum dewars, okay, picking up the aluminum dewars are things that you put liquid nitrogen in, and they had liquid nitrogen because they had these super cooled magnets, right? Picking them up and moving them through these magnetic fields was like trying to move them through molasses. Yeah? You tried to like, right? You have to like wrestle them through, and then what they do, and we'll talk about this again, I'll tell the same story over again, right? To pour this stuff out, they just tip it over on the side, and the magnetic damping forces would be so great that they just slowly kind of tip over, and the stuff would pour out of them, right? Okay? Now, if we were in this field, and we took a positively charged particle, right? And I threw it, right? This would be kind of funny, because it was a sufficiently strong field and there wasn't gravity, the thing would spiral around, wouldn't it? Right? And so the velocity would be that way, the magnetic field would be this way. Yeah? I'm flipping you all off and you're smiling, right? Okay? Right? The velocity would be that way, the magnetic field would be this way, and the force would be that way. So this thing would actually spiral around, and then of course, just like in that Dr. Seuss book, right? It hit me right in the back of the head or something like that, right? Where they see all the way around the earth and see the back of their head. Yeah. Okay, something like that, right? Okay, so, you know, there it is, right? This thing would spiral. Now let's suppose that there's no gravity or something like that, right? And I throw it, and I actually throw it not straight horizontal with the floor, but I throw it at some angle upward. Well, gee, the component of velocity that's parallel to that magnetic field, right, would really have no force acting on it, wouldn't change direction. And so that thing would actually, wouldn't it spiral around and around and go up? Wouldn't it? And if I threw it down, it would actually spiral around and go down. The important thing is that if you think of those magnetic field lines, the magnetic field lines would be going floor to ceiling, right? Yes? And any charged particle would actually be spiraling around those magnetic field lines, yes? Okay, now picture the Earth. The Earth's magnetic field lines go from the South Pole to the North Pole, yes, don't they? Right? So charged particles coming from the sun are actually going to spiral around those field lines, right? Because that's what they do. Charged particles spiral around field lines, right? And they're going to spiral, and it just depends on what the glancing blow is, right? And what the charge is, which way they spiral, right? But they're going to spiral, and in short, they're going to spiral toward the poles. Now, why is the radius getting smaller and smaller? Two possible explanations. Well, one is that the magnetic field is getting larger, and the other explanation could be that the velocity is getting smaller, right? It could be slowing down because it's encountering atmosphere. Probably it's getting tighter because the magnetic field is getting larger. The closer you get to the Earth, right? It's not a homogeneous magnetic field, right? So charged particles from the sun, when there are solar flares, right? I mean, solar flares are these pretty chunky things, right? I mean, there's big chunks of stuff that fly through space. If they strike a spaceship with astronauts on it, it's sort of like they get 1,000 chest x-rays right now, kind of a thing, right? I mean, it's, this is one of the things they're worried about if they actually send people to Mars is what happens if there is a solar flare and if that chunk of stuff hits the spaceship, right? But when there are solar flares, there's enough of these things that they fly down, they hit the atmosphere, and they strike the atmosphere. They do just what this zinc sulfide did, right? They emit light, and they'll emit light at characteristic frequencies, okay? So here are some pictures that I got off internet of northern lights, and they look like curtains. When you see them, they're like shimmering curtains because it's kind of like if you've ever watched a waterfall from below the water. Have you ever done that? Yeah. Like put mask on and swim down underneath a waterfall, and I don't know, I've done that because I'm always curious, right? It looks like that. The water striking down looks like this sort of like curtain-y thing. Like that. And that's, of course, what we're seeing is from below, we're seeing a waterfall of charged particles slamming into near the poles of the Earth, right? I have seen, and these things come and go with the solar sunspots. I believe sunspots cause solar flares, don't they? I believe that's what it is because the magnetic field actually erupts from the surface of the sun, right? The sun is plasma, yes? Yeah, plasma is basically... Plasma is a state of matter where the nucleus and the electrons are no longer tightly bound to each other, yes? The electrons go their own way, the nuclei go their own way. It's like a pot of charge, right? Do you expect plasma to conduct electricity with all those free electrons? Sure. Yeah, you bet. Plasma, the sun is like an enormous conductor. And the center, the poles rotate slower than the middle, is that right? Is that what it is? Does anybody know who took astronomy? It's something like that. They rotate at different rates, and so the poles rotate, or the equator rotates faster, right? And what that does is it's like a ball of rubber bands winding up, yeah? The magnetic field lines wind up and wind up and wind up, and every now and then, the magnetic field lines go sprawling from the sun, right? And they rearrange themselves, right? And that's what those big prominences are that you see when you see the images of the sun, yeah? Those solar prominences, and every now and then one of those goes snap, and it sends a big chunk of stuff that was in the sun, plasma, charged particles, flying toward the Earth, right? And that's what we're seeing here. And the sunspots are where those things, I believe the field lines are shooting out of the sun. They're relatively colder than the sun. So there's that. There's another one, right? And this is red stuff. I don't know, ask your chemistry teacher why it's red and why. I think one of them's nitrogen and one of them's something else, right? This is real typical, right? So I told you that ghost story about the one that I saw that looked like a rider with a lance on it. Okay, it was one of these guys that looked like a lance, like that thing, and you could kind of imagine that it would make kind of different shapes, and they'll sit there and shimmer and move across the sky. They're very, very. Has anybody ever seen Northern Lights? I've never seen them since in the 20 years I've been living out here. I've never seen them, but in the 80s there was a Northern Lights display that I could read by. It was the night sky there was no moon in the sky, and the Northern Lights were so bright that I remember getting a book out and going, okay, I'm going to remember that I can read this book by the light of the Northern Lights. Okay, and they were the green kind. I've only seen the green